and this will be the last concept of electrostatic forces. So far we studied about different concepts, but this will be the last concept, charge distribution. So generally the charge denotes with Q. Here we have a different types of distribution. Already we know about charge, that's a mass density. So mass density means mass is equals to, density is equals to mass upon volume. In the same way, if you want to represent the charge, so we are considering in three different formats. Charge will be distributed in three different formats. First one, so whenever we have a charge Q, we have a chance to move in a linear way through a voids. That's we call as a linear distribution. So whenever we consider linear distribution, so linear distribution means we will define this as a linear charge density. So linear charge density denotes with lambda. So it has a density of lambda and the charge will be distributed toward the length L. That's a lambda is equals to density is equal to mass upon volume. Instead of mass we will consider here a charge. Charge upon volume, charge upon length. This will be the first one. If you consider second one, charge with respect to 2. Here we consider a sheet. Here we consider a sheet where we have a length and breadth. So whatever the charge we are considering, it was distributed through a length and breadth, and here we are giving the name as a sigma. The second one we call as a linear. Here length into breadth will give us the area. Length into breadth will give us the area. That's we call as a area charge density. So area charge density denotes with sigma. Sigma is equal to again charge upon area. Okay. And third one, so here we consider third pattern. We consider one cuboid. So whenever we consider a cuboid, there we have a volume. So this we call it as a volume charge density. Volume charge density. Here it denotes with rho. So again rho is equals to the same formula. Charge if you consider linear, charge upon length. Charge if you consider area, charge upon area. So here charge upon volume. So how we can define the volume? Here we have a length, breadth and height. So length into breadth into height will give us the volume. This will be the third one. So charge is distributed in three patterns: linear charge, areal charge, volumetric charge. That's a volume charge. So linear charge denotes with sigma Q by L. Area denotes with sigma is equals to Q by A. Volume denotes with rho is equals to Q by V. So we studied about three types of distributions. The first one, linear charge distribution. What's the formula for linear? It denotes with lambda. Lambda is equal to charge upon length. And if you consider next one, area charge distribution, it denotes with sigma. Sigma is equals to charge upon area. In some cases we will define charge upon surface. Okay. And third one, volume charge distribution. It denotes with rho. So rho is equals to charge upon volume. So these are the three definitions. And next concept, we have a Gauss theorem, and this will be very, very important for your exam point of view. Here, to define the Gauss theorem, first we have to know about electric flux. So already we studied about electric flux. So electric flux, which denotes with phi. And what's the definition for electric flux? Number of electric field lines passes through the given surface area. That's the flux is equals to EA. Both are having same direction, or we can represent flux is equals to EA cos theta. So already we defined these definitions, and this definition is applicable only for uniform electric field lines. It's applicable only for uniform electric field lines. Suppose if you have a non-uniform, so non-uniform electric field lines, then flux is equals to surface integral. Surface integral flux is equals to surface integral E dot ds. So instead of area we will consider as a ds. I will explain this concept again in the clear definition. That's in a Gauss theorem. Just we are defining only a uniform and non-uniform. Surface integral of E ds dot cos theta. So this will be for uniform and other will be a non-uniform. Whenever we want to define non-uniform, then we have to represent this formula, and whenever we represent uniform, we have to represent this formula. Okay, so actually we have to start Gauss theorem, but instead of Gauss theorem we represented the concept of electric flux. So why we represented electric flux means, so next definition we have a Gauss theorem. And before Gauss theorem already we know when will be the flux will be a maximum, when will be the flux will be a minimum. So already we know these definitions. When electric field lines and area both are parallel to each other, then the flux will be a maximum. Similarly, when E and A both are perpendicular, the angle will be a 90 degrees, then the value will become a 0. Already we studied maximum and minimum. Now we have a Gauss theorem, So what is the Gauss theorem means? The total number of, the total electric flux through any closed surface is equal to the 1 by epsilon naught times of the net charge. Net charge enclosed by the surface. So that's Gauss theorem. The total electric flux through any closed surface is equal to the 1 by epsilon naught time of the net charge enclosed by the surface. Simply, so we have a flux is equals to the total number of flux passes through any closed surface. So not only cube, so we can consider circular part, we can consider any random shape, whatever it may be the shape, but it should be a closed path. Then the net value is equals to 1 by epsilon naught of net charge. So this will be the Gauss theorem. Now we will derive the expression and we need a proof. So we need a proof means already we have a Gauss theorem, already we know about electric flux. So whenever we consider the applications of Gauss theorem, then these three lines will be applicable. That's a linear, area and volume. So for Gauss we have three applications. In the three definitions we will use. Next, in Gauss theorem we want to define the electric flux. So what is the electric flux means? The number of field lines passes through the given surface area. If it is a uniform, flux is equal to EA cos theta. If it is a non-uniform, surface integral E dot ds cos theta. Next we will check the proof for Gauss theorem. Okay, so here we have a statement. So based on this statement we have to prove flux is equals to 1 by epsilon naught of charge. So here we have a derivation, that's a proof. Initially we consider one circular object, the central point to the surface. So we have a total surface S. And from the center to the surface we have a radius R. Suppose instead of calculating overall surface, so we are considering the small area here. So we are considering the small area. The small area we represented with delta S. Okay, so these are the terms according to a electric flux. So flux is equals to, it's a non-uniform. So non-uniform means all are moving in different direction. So non-uniform electric flux, surface integral of E ds cos theta. So surface integral, either we can represent delta or ds, both will be the same. So ds cos theta. Here radius R and small element ds both are parallel to each other. Then what will be the angle? Theta is equals to, then angle theta is equals to 90 degrees. Sorry, theta is equals to 0 degrees. So 0 degrees means we get the maximum. So we get the maximum. Then flux is equals to surface integral of S E ds. Cos 0 is equals to 1. So we get the flux. We get the flux. Now, what will be the area of circle? So area of circle is 4 pi r. So area of the circle is 4 pi r. So area means, so whenever we are applying integration, flux is equals to, E will be the electric field which is constant. So integration of surface integration of ds. So integration differentiator cancel, we get the value of circle. That's the surface. That's E into 4 pi r square. And what is the value of E? We know the value of E is equals to 1 by 4 pi epsilon naught into Q by R square. So already we know about electric field into 4 pi R square. 4 pi R square cancel. So finally we get flux is equals to Q by epsilon naught. So this will be the proof for Gauss theorem. So already we proved the Gauss theorem. Here we have some points to be reminded. So Gauss theorem is true for any closed surface irrespective of size and shape. So whatever it may be the shape and whatever it may be the size, the Gauss theorem is true for any closed surface. So closed surface means we need a complete one rotation. And second point, in equation phi is equals to Q by epsilon naught, where Q stands for sum of all charges enclosed with the surface. So whatever the surface we consider, wherever it may be the charge, so we have to add all the terms so that we get the Q value, that's a net value. And third one, if a Gauss surface is so chosen, the charge lies inside and some outside. So some inside, some outside means, so generally this will be the content. So whenever we consider Gaussian surface means, so we have a imaginary surface around the point. Either we will consider outside or inside. So if a Gauss surface is so chosen that the charge lies inside and some outside, then the flux, both inward and outward. So inward and outward means, inward direction means positive charge, outward direction means, inward direction means negative charge, outward direction means positive charge, will be 1 by epsilon naught times of the net charge enclosed by the surface. And it will be cleared more in example. So we have to remind these points. Along with these 3 points, we have an applications of Gauss theorem. So first application, field due to an infinite long straight uniformly charged wire, field due to an infinite plane sheet, field due to an charge conducting spherical sphere. So here we have 3 applications. So we will derive each and every application. So next one, a first application of Gauss electric field due to an infinite long straight conducting wire. So we have to derive an expression for this. Straight wire means, so consider we have a one straight wire. So whenever we consider a straight wire, the wire is in circular format. So circular format means, so we will consider this as like a tube. Consider like a tube. Okay. So consider like a tube. Suppose consider it has a length L. It has a length L. We consider this is a positive charge. So we place some positive charge. That's infinite. Consider it will be an infinite length. Now, whenever we want to define the Gauss theorem, for this we need a Gaussian surface. So for Gauss theorem, Gaussian surface. Gaussian surface is nothing but, so we will consider some imaginary circle. So whatever the tube we consider, we will consider some imaginary tube. So imaginary tube means, consider this was the ripple, this will be an inside packet part, or we consider wire. So inside we have a wire, at that we have a coated laminated. So this will be an imaginary part. So imaginary part we have a length. Here we consider a Gaussian surface. This we called as a Gaussian surface. Suppose if you consider here we have a positive charge, means the positive charge moves in a straight line, and here we consider uniform. So uniform means the field lines will becomes in this direction. So this will be the direction of field lines. So we are considering this will be a uniform. Okay, so to define Gauss, we know we want to define the flux. So to define the Gauss, we have to know about electric flux. So electric flux means number of field lines passes through the given surface area. So for this we are considering three surfaces. So at the top point we consider one area, this will be a ds1, and the bottom point we consider one more, this we consider ds2, and whenever we consider the side parts it will be a curved path. So here also we consider some hole. Here also consider we surface, this will be a ds3. So to define the Gauss theorem, we consider three surfaces. So let ds1, ds2, ds3 are the three surfaces we consider. Okay, so before we want to define the Gauss, we need an electric flux. What is the electric flux? Flux is equals to E A cos theta, or flux is equals to surface integral of E ds cos theta. So we have three terms. So here we have a calculation of, we have a chance of calculation of three flux. So for ds1 we get the flux 1, flux 2 and flux 3. So what will be the flux 1? Flux 1 is equals to, what will be the flux 1? So here we have a surface integral of S E ds cos theta. So what will be the angle between field lines and ds, angle made by them is 90 degrees because the area represented in upward direction and field lines will be in downward direction. Both will be a perpendicular. So 90 degrees. If you consider second one, these are the field lines and the area will be represents downward direction. So angle will be 90 degrees. And here whatever the area we consider and field lines both are of same direction, then angle will be a 0. So for first one, theta is equals to 90 degrees. So we get the value flux 1 is equals to 0. Flux 1 is equals to 0. Similarly, flux 2 is also we get 0 because E ds1 and ds2 both are perpendicular to each other. The value is 90 degrees. So we get the values E phi 1 and phi 2 is equals to 0. At the end we have a flux 3. So flux 3 is equals to, here integration of EDS we have a formula. So where E and ds3 both are making an angle of 0. So cos 0 is equals to 1. So we get flux 3 is equals to integration of E ds3. E ds3 cos 0 is equals to 1. Cos 0 is equals to 1. So what will be the net flux? Net flux is equals to flux total is equals to flux 1 plus flux 2 plus flux 3. So what is the flux 1? So what is the flux 1? 0. The total flux is equals to flux 1 0, flux 2 0 and flux 3 will be surface integral of E ds3. So total flux if you want to calculate. So total flux is equals to E into surface integral of ds3. So what is the surface integral of a line wire? Area of a wire. So area of a wire will be 2 pi r L. Substitute that. So we get E into 2 pi r L. This is the total flux. So equation 1. And according to Gaussian, so we have a Gaussian, according to Gauss theorem, flux is equals to 1 by epsilon naught of charge. Here we have an equation 2. Here we have an equation 2. So equating 1 and 2 expressions, equating 1 and 2. So if you equate 1 and 2, we get 1 by epsilon naught q is equals to E into 2 pi r L. This is the value of equating. So we get the value of E here. So what will be the E? So E is equals to q by epsilon naught 2 pi r L. So this will be the electric field due to an infinite long wire. But the concept is about linear. So linear charge we have. And linear charge denotes with lambda. So lambda is equals to charge upon length. And what will be the charge? Charge is equal to lambda into length. Substitute this value in the above expression. We get E is equal to charge we get lambda into L by epsilon naught, that's a 2 epsilon naught pi r L. So L will be cancelled. At the end we get the value of E is equals to lambda by 2 epsilon naught pi r. Along we have some x direction. This will be the electric field due to an infinite long straight conducting wire. So initially we consider a wire which has a positive strength, and we consider some imaginary line for this wire that we called as a Gaussian surface. At that Gaussian surface we consider the three layers, three surfaces: surface ds1, surface ds2 and surface ds3. So whenever we have a positive, the positive radiates the field lines uniformly. So we are considering three surfaces ds1, ds2 and ds3. For that we get flux 1, flux 2 and flux 3. Suppose if you consider flux 1, where the area will be in upward direction and surface will be, that's the field lines will be in perpendicular to that surface. Similarly, if you consider surface 2, the surface 2 also, which was perpendicular, that's a 90 degrees. So surface 1, surface 2 will become a 0. But if you consider surface 3, there ds3 and field lines both are same direction, then theta value will be equals to 0. By substituting this theta value, we get the value as sigma E ds3. Sorry, so integration E ds3. So we need a total flux. Total flux is equal to summation of all the three flux. Flux 1 is 0, flux 2 is 0, we get the flux 3. So whenever we consider the linear, so linear means the area of wire will be a 2 pi Rn. So we substituted those values, we get the total flux is equals to E dot 2 pi Rn, equation 1. According to Gauss theorem, we have an expression 2. We substituted, just we compare the equation 1 and 2. We get the expression as E is equal to Q by epsilon 2 pi Rl. But we have three definitions we discussed. Linear density, in that we have. So linear density means sigma is equals to, lambda is equals to Q by L. So Q is equal to lambda L. So we substituted the value of Q in the above expression. We get E is equal to some term. So in that L will be cancelled. Finally we get electric field in a closed infinite long wire is equals to sigma by 2 pi epsilon naught R along the x direction. Second one, electric field due to an infinite long sheet. So we consider a paper. In that we placed a small hole, and we consider a Gaussian surface. This will be a imaginary surface. Gaussian surface is nothing but imaginary surface. Okay, so it's just like a cube. So whenever we consider some charge, so it will be radiated. Suppose here we have some positive charge. The positive charge will be moved in this direction and in this direction from the center. And to define the Gaussian surface, here we are considering three surfaces. At the edge, here we consider one hole. At the top point we consider one hole. At the down point we consider one hole. And other side we consider one hole. So this will be a area 1. Here we have a length into breadth. Area 1, area 2, area 3 and area 4. So all areas we considered equal. That's a A1 is equals to A2 is equals to A3 is equals to A4. Okay. Now to define infinite long sheet, again the same process. To define the Gauss, first we have to calculate the electric flux. So what is the formula for electric flux? Flux is equals to E A cos theta. Clear? So we are using with respect to area. So here we have a area 1, area 2, area 3, area 4. We consider 4 areas. All areas will be a equal strength of A. So for this we get the flux 1, flux 2, flux 3 and flux 4. So already we know about flux. For example, if you consider first flux, so flux 1 is equals to, flux 1 is equals to means, suppose if you consider this is a positive, it will be end set negative. That's area 1 and field lines. Area and field lines. Both are of same direction. That's theta is equals to 0. So theta is equals to 0 means we get flux 1 is equals to EA cos 0. So is equals to EA. That's a flux 1. Similarly, if you consider a 2, flux 2 is equals to, where if you consider flux at the top layer. So top layer means this is the whole direction and this is the direction of hole and this is the downward direction and this will be an upward direction. So if you consider the directions, so again we will represent easily. So if you consider the based on directions, if you consider first one, E and A both are same direction, then theta value will be equals to 0 for first one. For second one, E and area 2 both are perpendicular, the theta will be 90 degrees. E and area 3 is also perpendicular, theta value 90 degrees. E and A4, theta value 0 degrees. So we want to calculate the flux. So flux total is equals to flux 1 plus flux 2 plus flux 3 plus flux 4. So what's the formula for flux? EA cos 0 plus EA cos 90 plus EA cos 90 plus EA cos 0. So cos 0 is equals to 1, cos 90 value will be cancelled. We get EA1 plus EA. So we get total flux is equals to 2EA. So we get the total flux. But according to Gaussian theorem, flux is equals to 1 by epsilon naught of charge. And we are taking this as an equation 1 and this will be an equation 2. By comparing equation 1 and 2, we get 1 by epsilon naught of charge is equals to 2EA. So we want to calculate the value of E. So which implies E is equals to Q by 2 epsilon naught A. This is the value of electric field for a long sheet. But according to volume charge distribution, according to area charge distribution, what's the area charge distribution? Which denotes with sigma. Sigma is equal to charge upon area, which implies charge is equals to sigma into area. Substitute the value, we get E is equals to sigma into area by 2 epsilon naught into A. So sigma is A will be cancelled. We get electric field for a infinite long sheet will be E is equal to sigma by 2 epsilon naught along the x direction. So last one, the last application of Gauss theorem, electric field due to an spherical sphere. So initially we consider one sphere. It has a radius r. It has a radius r. So already we calculated this. So for this we will consider, first we will derive the statement. This already we derived for a Gaussian theorem. So how we define the Gaussian theorem? So we have a flux is equals to so integration, surface integration of E ds. So both are having a directions. We get surface integral of E ds cos theta. So we have a formula. So here we consider the small sphere. So in that, suppose if you place the small area here, so from this we get some field lines. So surface we consider as a ds. So the flux, if you represent it, flux is equals to E will be a constant. So integration of ds, and here radius and ds both are having same direction, which implies theta is equals to 0. So we get cos 0 is equals to 1. For a sphere, since for a sphere ds is equals to 4 pi r square. Substituted that, we get flux is equals to E. Already we know the value of E as a 1 by 4 pi epsilon naught q by r square into 4 pi r square, or leave this expression directly. So E into 4 pi r square. So 4 pi r square, just this is the expression. We get 4 pi r square will be cancelled. Just wait a minute. Sorry, just don't consider this term. So we have a flux is equal to E ds value. So what is the value of flux? The flux value is a 1 by, according to Gauss, flux is equals to q by epsilon naught. Substitute the value. Substitute the value means we get q by epsilon naught is equals to E into surface integral of ds. Surface integral of ds means we get q is equals to E 4 pi r square by epsilon naught, which implies what is the value of E? E is equals to 1 by 4 pi epsilon naught r square into q. So we get the field lines. We get the expression of electric field. So we get the value of E is equal to q by 4 pi epsilon naught r square. But in this, remind this expression. So this will be the useful expression for this derivation. Okay, so we have a little bit confusion, but don't worry, I will give you a clarity. So initially we considered this is the sphere. This is the sphere. We have a radius r, and we placed a small hole here. We placed a small hole here with ds. So whatever the field lines, we will be radiated out. So what will be the field length? It will be radiated out. So whatever the field length, it will be radiated out with the small hole. But to define electric field due to a spherical, we need a Gaussian surface. So Gaussian surface means we consider one Gaussian surface. So Gaussian surface means we are considering an imaginary surface. So this is an imaginary surface. Consider the imaginary surface has radius capital R. Radius capital R. From the above expression, it was clear R is more when compared to smaller. Whatever the original surface we consider, that surface is less when compared to the Gaussian surface. So whatever the radiations, it will be the number of field lengths passes through the given surface area, it will be a present, but it won't cross the Gaussian surface. So it won't cross the Gaussian surface. So according to the above expression, integration of E ds is equals to q by epsilon naught we have. So whatever the charge, it was inside. So it was q is enclosed inside. But q is enclosed with inside means the net value will be equal to 0 because there is no flux here. There is no flux at the end. So there is no flux at the end means the charge will be enclosed, the value will become a 0. So we get, so integration of S E ds is equals to 0, which implies electric field is equals to 0. So this, whenever we consider a field inside, so Gaussian surface will be outside, whatever the sphere we consider, it will be inside. So this will be the inside sphere. First one, inside sphere, the electric field will be equals to 0. Electric field is equals to 0. Now we will consider the second one. The same. Here we consider the Gaussian surface. We consider the sphere. It has a small radius r. Now whatever the surface we consider inside, thus we have a Gaussian surface we consider inside. This will be the Gaussian surface. That we call as the imaginary line. It has a radius of capital R. So second one we consider it outside. The sphere will be outside. Inside we consider as a Gaussian surface. For this, R value is more when compared to R. So if you consider R, the R value will be a more. So whenever we consider a small hole here, small ds, so whatever the field length, it will be passes through this point. So it will be not an enclosed. So we consider the overall surface. So for this, the expression will be surface integral of E ds is equals to q by epsilon naught. So surface integral means we have a formula. So inside the surface, ds is equals to 4 pi r square. So we need a value of So integration of ds is equals to 4 pi r square. Substitute the value, e into integration will be 4 pi r square is equals to q by epsilon naught. So which implies e is equals to 1 by 4 pi epsilon naught q by r square. So this will be the field of a sphere if you consider outside. If you consider inside, the value will become a 0. If you consider outside, we get the value. Suppose the same concept if you consider just before and just after the boundary. Just before, just after the boundary means the same answers we get. So whatever the sphere we consider, if you consider Gaussian surface inside, if you consider Gaussian surface inside, just note, just inside. So just inside, just outside. Just inside means we get the value, just outside means the value will become a 0. So whenever you practice this, you will get the clarity. I hope it was clear. But this will be the end of your topic of electric field, electrostatic forces. For the next video, we will define a numericals based on all these concepts. So one more video is pending. So only for numericals. And practice all these derivations. I given a basic idea, but go through your NCERT books or whatever the material you prefer. But practice all those derivations. And if you have any doubt, just make a comment. Thank you.